This lecture will be a little heavy on the math side because number theory is important to how cryptography works. But don't be too concerned. We'll just cover some basic principles of number theory, and I'll leave the more in-depth version to the textbook and your own personal study. I want to give you good foundation on the math behind cryptography, cover modular arithmetic, and discuss how a simple operation can make cryptography so secure. So here's a little math refresher for you in case you have been away from math classes for a while, which is pretty common in a 400 level course. These are terms you will encounter in your textbook over the next few weeks, and if you dig further into cryptography, you will see these terms even more often. So knowing what they mean will help you understand what the different textbooks and websites provide. A set is a collection of elements denoted by being enclosed in brackets. Anytime we see numbers inside of brackets, like you see on the first bullet point, it represents a set of numbers. We can also use ellipses in place of the numbers to show that the set continues in the same direction. An element is any single part of a set. This is denoted by a funny looking E, which is really the Greek symbol for a lowercase epsilon. So in the second bullet, we see that the number 1 is an element of the set that follows the epsilon character. The 1 in this case could also be a 0 or a 2, and it would be a correct statement. And within math formulas, the letter N typically refers to the natural set of numbers, which are whole numbers and are not negative. The letter Z is also used in math to represent the set of all integers. That's positive and negative whole numbers, and it also includes 0 in this set, even though it isn't positive or negative. Note that whole numbers do not include fractions, and that this set goes on to infinity in both the positive and negative direction. If you want to represent a set that includes fractions, the letter Q is typically used as that variable, and it represents the rational numbers. Rational numbers are fractions that have a whole number in the numerator and the denominator. Now, you won't see this again in these slides, but if you look at the equations that make up many of the cryptographic functions and algorithms, you will come across these variables, and the representation here is pretty common in those algorithms. So having a basic understanding of what they stand for could make deciphering the equations in the textbook a little easier. And it's also important to understand these core math definitions, as these basic principles show up in cryptography all the time. Now on to modular arithmetic. You may have never been exposed to this form of math before, because most math used in the United States is the base 10 form that we all learn in our early days of elementary school. Modular arithmetic is completely different because the work of addition and subtraction happens in a circle instead of the straight left to right line that you are used to. If you picture the face of a clock, you can see that whenever the hand strikes 12, the number resets back to 1. Modular arithmetic works the same way in that the values wrap around a fixed number that we call a modulus. So looking at the clock again, the modulus would be 12, because that is the point where all the values wrap back to 1. So if you had a simple operation like 9 plus 8, normal math would tell you that it equals 17. But in modular math, with a modulus of 12, it would only equal 5. This is because once you arrive at the value of modulus, you have to start back at 1 and then continue counting. This brings us back around to 5. And it also works in the reverse order. 5 minus 7 would equal 10, because as you count backwards on the circle, you will hit 12, and continuing on 2 more spaces will bring you to 10. It's a little confusing at first, but if you use a clock face as you think through this, it will start to make sense. The reason these modular math concepts are so important for you to understand in this course is because modular arithmetic is used in cryptography. One of the more common methods of exchanging encryption keys over the insecure internet is a method known as the Diffie-Hellman exchange. Diffie-Hellman allows two users to create a key on the fly and share those keys with each other by performing mathematical operations on each user's computer. Simply put, each user chooses a few different numbers as variables. Some of those numbers are shared in clear text over the internet, but one of them remains a secret to each user. This secret variable is what provides the security of the operation in a similar manner as a secret key. One of the variables is used as the modulus, and it is such a large number that it is extremely difficult and almost impossible to mathematically discover. The math itself is quite simple once you understand modular arithmetic. And this isn't some 40-page calculus equation thought up by Albert Einstein. It's a simple equation that anyone can understand. Your textbook provides the entire algorithm and each part of the operation for you to examine more closely. If someone is listening in on the conversation by monitoring your network traffic, they will be able to see every chosen variable except the secret one selected by each user. So you might think that with most of the variables in hand and knowledge of the equation, an attacker could simply reverse engineer the math and figure out the missing numbers. But because the modulus is so big, there is no computer in existence today that could store all the possibilities. So it would not be able to successfully compute what the secret variable is. This makes the Diffie-Hellman key exchange incredibly strong and allows two users to communicate securely. But this key exchange is simply the first step in the operation. This process creates the keys that the users will use to encrypt all future communication. It is more than likely that you use secure websites on a regular basis. Anytime you visit a site that starts with HTTPS, your data is encrypted. This is the most common with online merchants, so that your purchase information is secure, and also with banks so that your account information remains private. But there is a movement to make as many websites encrypted as possible, and while it's doubtful that will happen anytime soon, this key exchange protocol we just discussed is one of the common methods keys are generated for encrypting this web traffic. Each time you visit a secure website, a key exchange takes place in the background when the connection is established. This happens for every session, so every time you visit that site, you will use a different key. This helps to keep a user secure because if somehow a hacker did gain access to your key, it would change on the next session, and the old one would become worthless. And Diffie-Hellman is just one of the common methods in use. RSA uses a different form of math, but can also be used in a key exchange process. And some mathematicians are working on algorithms that will be strong enough to survive in a theoretical quantum computing world, just in case that day ever arrives. Diffie-Hellman was created in 1976. And recent research in 2015 has shown that any Diffie-Hellman exchange smaller than 2048 bits is subject to successful attack. We can chalk this up to computing power greatly being increased since the 1970s. The solution for this problem was to use a larger prime number that is at least 2048 bits in size. It's not unreasonable to think that an encryption capability created 40 years ago would have difficulty surviving in today's computing world. But the math behind the method continues to win out, and as long as the numbers are large enough, computers will continue to be unable to break the method. I suspect that as computers continue to get faster, we will need to increase the bit size even further to keep up with technological advances. Here's the big takeaway. Simple mathematical functions can be used to provide a great deal of security, and even though they are simple to use when generating keys, they are much more difficult when trying to reverse the order. None of this math could be done on paper with the size of the variables used in these operations, but you could practice the equation using smaller numbers on your own, and you will see that it works quite well. It's actually very interesting that an operation by one user can yield the same result as an operation by another user, even when one of the variables is completely different. Modular arithmetic is probably new to most students because it is not a common lesson in elementary or high school classes, but in the world of cryptography it is very common. And this simple math function has given us years' worth of strong security, and it will likely continue into the foreseeable future.